All right, we're going to start our last section of Unit 2 today, 195. It's going to be kind of a review unit where we're going to have a bunch of different questions or problems from all of Unit 2, so well, not necessarily all of Unit 2, but the second half of Unit 2 that we've been dealing with. So this is going to be a really good section for us to kind of bring everything together. Plus note, okay, bonus note for this for this unit, this section, there's no homework for this section. It's just meant to be kind of a review section. So we're going to see if we can bring everything together to help us with these types of questions. We are going to need a calculator today, like I said, so make sure you have one. We're going to be doing some graphing. All right, looking at our first one. The graph of a cubic function in this form, they don't really tell us an equation, they just know a general setup of the equation, is pictured to the right. So, part A, based on the graph, can we make any conclusions about the A number and the D number from the equation? Yeah?
We can determine D number by looking at the y-intercept.
Okay, so you can determine D exactly. So y-intercept would be 1. Right, so we can figure out that one exactly. Can we conclude anything about A? We might not know it exactly, yeah.
Based off the fact that 1 is D, you might be able to use the x-intercept to determine that, because you have 1/2 as your x-intercept, you might be able to determine A, like using the multiple.
Are you sure this is 1/2?
Well, okay, that's fair enough.
Okay.
It's negative
How do you know A is negative?
because the right side goes down.
Right side falls. Good. Right side falls. Okay, so we know D exactly, and we know something about A. We'll eventually try to figure out what A is, okay, but at least we know it should be negative. So far, so good. All right, B. Based on the graph, what can we conclude about the roots, zeros, x-intercepts of the graph? Travis was kind of mentioning this x-intercept earlier. Might be 1/2, we're not sure. Do we know something about that root? Yeah?
It's positive, or it's on the positive side.
Positive. Okay, so we have one positive root with multiplicity of 1. Okay. Can we conclude anything about the other roots? Yeah? Why do you know? Okay, so if we think about all of our possibilities, either positive, negative, origin, or imaginary, based off the graph, we can see we only have one positive, no origin, no negative. So the other ones are imaginary. How many are there? 2. Good, because we're cubic. So we can see one of them, which means the other 2 that we need to have are imaginary. Okay, they're not graphable. Looks good. Explain your reasoning. We'll say we can see this. We can't see these. Also, we'll say degree of 3. So we know we have to add up to 3 somehow. We can see one of them, which means the other 2 are imaginary.
That's nice.
So far, so good? Okay. Part C. Based on the graph, what is the maximum number of sign changes that the g of x equation from the top could possibly have? This is a thinker. Yeah.
Just 1,
Why?
because there's only one positive root, so there can only be one sign.
Okay, so we know that there's only one positive, okay? But when we did Descartes' rule of signs, something gave us the maximum number, and then we were able to figure out other possibilities based off of that. So we know there's one, but we're trying to figure out the maximum number. This is the actual one. Can we figure out other possibilities? Yeah?
There could be three if it was alternating between positive and negative.
Okay, so if we look at how many terms we have up here, we already know A is negative, and we know D is positive. So what's the maximum number of sign changes we could have here? The maximum number would be if every single one alternated, right? So this would be negative to positive, which would be 1, positive to negative, which would be 2, and then negative to positive, which would be 3. So if we look at the equation, I know it says based off the graph. We'll talk about that in a second. But based off the equation, if those are the only terms we have, the maximum possibility would be 3. So we'll say based on equation, the most would be 3. Okay? But how can we conclude that from the graph? I know that's a good thing to look for, but the question itself is saying based on the graph. So we know that there should be 1. Okay? How can we figure out other possibilities? Yeah?
Like 3 or 1 because it can only go by 2.
It can only go by 2s. When we did Descartes' rule of signs, remember how we subtracted 2 to figure out other possibilities? Well, in this case, we know it's 1, so if we add 2, we can figure out the maximum number of sign changes. It's kind of working backwards. So based on the graph, the 1 x-intercept could also produce 3, 5, 7, 9, okay, etc. sign changes, okay, in the equation. But if we look at the equation itself, we only have so many terms, and we also know that the degree is 3. So there's no way we could have 5 sign changes, because that would mean we have a possibility of 5 x-intercepts, and we can only have at most 3. So it's kind of using Descartes' rule of signs backwards, if you will, as kind of a thinker. So 3 is the only, we'll say, logical one based on the degree. Can we see that? Can we understand that? Descartes' rule of signs backwards. We're starting with an actual x-intercept, but if we add 2, now we can figure out how many sign changes in the equation we have. Yeah?
Just based on the graph, we don't know the degree, right?
No, but they're telling us, we're kind of using these in conjunction with each other. I know it says based off the graph, so we're going to start here, but we do have to use them together to help us narrow it down. But you're correct. If we did have the equation, we wouldn't know. It would be 3, 5, 7, 9, whatever. All right. Speaking of the equation, let's see if we can actually figure it out. So we already know what D is. We already know something about A. It should be negative. Let's see if we can figure out the other values exactly. So they're telling us as little hints or clues here, if the coefficient of the linear term is -3, and g of -1 is 8. Somehow we're going to use that information to help us find the equation. You have an idea, Travis?
Is linear term the one with the x to the first power?
X to the first. Okay, so in the equation, x to the first, the coefficient is c. So we can go ahead and write -3 in for that c. So we don't know what a is. We know it's negative, but we don't know what it is. They're telling us that the c coefficient's -3, and we'll go ahead and put in +1 for our d. All right, so we use the -3 information. How can we use the g of -1 equals 8? Can we think about what those numbers represent? What do you think, Lainey?
All the x's will be -1 and the y
There we go. Okay, we can plug in the point. So 8 equals, if we plug in -1 for the x's, -1 cubed would be negative, -1 squared would be positive, -3 times -1 would be a positive 3, and if we add 1, we'll get 4. So maybe combining some like terms, if we subtract the 4 over, we'll get 4 equals -a plus b. So I like this. This is the information that they're giving us. It's kind of leading us into something. But notice how we have one equation with 2 variables. We can't really figure out what just A is and what just B is. So there might be something else we have to do. Yeah?
Would we be able to use a system for this? Like,
Uh-huh.
So would like the fact that 0, 1 are zeros?
Okay. Maybe we can use another point. So notice how if we have one equation with 2 variables, we can't solve it. So somehow we got to think of another equation to use to develop a system to help us solve it. So if we use the point 0, 1, if you were to plug in 0 for all those x's, that would get rid of a and b. So, I mean, it's an easy point to use, but it won't help us, unfortunately. Can we think of another point, though, that we can use?
Oh, yeah, that works too.
Maybe I'll erase these. Can we find another good point? Yeah? 1, -2. All right, so if we plug in -2 for y, and then 1 for all the x's, a plus b, we'll have -3 plus 1, which would be -2. And then combining like terms, we can add the 2 over, we'll get 0. Okay. So unfortunately, the information they provided to us was great, but it wasn't enough for us to figure out what A and B were on our own. Okay, we had to take the initiative, that extra step, to try to figure out another equation. And now that we have a system, let's figure out what A and B are. So it just depends on your personal preference. Do we prefer elimination, substitution? What do you want to do? You want to do substitution? Okay, so pick a variable, pick an equation, and we'll solve for it. Do you have a preference? Completely up to you. Maybe this one, I'll subtract the A over. So B equals -A. I'll plug that in here. So divide -2, we'll get 2. Oh wait, this shouldn't be negative. So this should be negative. All right. Can we figure out what B is? Maybe we can plug it back in somewhere. If the opposite of A is B, the opposite of -2 would be +2. Okay, so we know what A is, we know what B is. They told us what C is, and we figured out what D was from part A. So we can go ahead and write our equation. We'll have -2 x to the third plus 2x squared minus 3x plus 1. Is our A value negative, like we anticipated from part A? Yeah? How many sign changes do we have? Negative to positive, positive to negative, negative to positive. We have 3. Like we can't kind of anticipated for part C, at least the maximum number at least. So it seems like everything's working out like we anticipated from these questions. We're doing okay so far? Yeah? Okay. Let's go ahead and try another one. Consider the quartic function, okay, power of 4, to answer the following questions. Use Descartes' rule of signs to create a chart of possible combinations. So we're going to have to roll through our list of negative options, positive options, origin options, and imaginary. All right, Descartes' rule of signs. Looking at the original problem, the original function, how many sign changes can you identify? 2. All right, looks like we have negative to positive, and then positive to negative. So at most 2 positive x-intercepts are on our graph. If we subtract 2, another possibility would be none. Maybe we don't have any positive x-intercepts. All right, so that's just our positive options. If we wanted to figure out negative options, we have to look at a new equation if we were to plug in negative x in for all the x's. Can we think about how that would change our equation? Can we kind of quickly pinpoint which terms would change but which ones would stay the same perhaps? What do you think, Blair?
Only the linear one changes
Okay, and why only this one?
because it's the only one with an odd power.
Odd power. Okay, odd powers change because if you have an odd amount of negatives, it's going to become a negative or become an opposite. So negative x to the 4th stays, positive 3x squared changes. This is going to become a positive 2x, and then minus 2 stays the same. So in this new equation, how many sign changes do we have? Can we find them? Yeah? 2. Okay, between the first 2 looks like and the last 2. Okay, so we have at most 2 negative x-intercepts, but another possibility if we subtract 2 would be 0. Okay, maybe we don't have any. That's Descartes' rule of signs. Okay, just looking at the positives and the negatives for those sign changes. Can we determine if we touch the origin at all? We do not? Why not? We have that constant on the end. Okay, so that's prohibiting us from having x as a GCF. We can't factor out an x, which would in turn result in an x-intercept of 0. Okay, so x is not a GCF. What about our imaginary possibilities? We have that buddy system. Yeah?
Could be either 4, 2, or 0.
4, 2, or 0. Okay, degree is 4. That's an even number, so we can include it. Maybe all x-intercepts are imaginary. But if they show up in pairs, 2 is an option, and then maybe we don't have any at all. Okay, so if these are all the possibilities where x-intercepts can be located, we're going to develop our chart of all the different combinations. Can we list some? Let's see, I can have 2 positive, 2 negative, none at the origin for sure. And if my degree is 4, that would leave me with no imaginaries because I already have the 4 covered. Can we find another one? Good, Caitlin?
2 positive, 0 negative, 0 at the origin, and 2 imaginary.
I like it. Okay, so 2, none, none, 2. That checks out. Any other ones? Keep going, yeah.
0 positive, 2 negative, 0 at the origin, and then 2 imaginary.
Works out. Okay, 0, 2, 0, 2. Good. Any more? Good, Noah? 0004. Okay, so no positive, no negative, none at the origin, so all 4 of them must be imaginary. Is there another one? No, that's it? Okay. So there's our list of possibilities. We're going to go ahead and graph it for part B to kind of confirm which of the 4 is the actual combination. So on our calculator, we'll go ahead and hit y equals. Go ahead and type it in. It might already be in there because we did this first period as well. So go ahead and type in your equation. And before you hit graph, go to the window button and program in the -4 and +4 like it's on your paper for your grid. All right, go ahead and hit graph. If we try to draw this as accurately as possible, maybe we can plot where some x-intercepts are located. We know the y-intercept's -2 because that's our constant term. Looks like this first kind of high point is at a height of almost 3. And then we have this little kind of hump and bump movement towards the bottom. Something like that. Okay, so rough sketch, maybe something like that. So now that we have a picture, can we decide which of the 4 combinations is the correct one? What do you think, Noah?
2 positive, 0 negative, 0, 0, and then 2 imaginary.
Same again, 2.
2 positive, 0 negative, 0, 0, and then 2 imaginary.
I don't know if we did you? Did you remember the negative out front?
Yeah.
Okay, maybe check it again. Yeah, Caitlin? 2 negative, 2 imaginary. Okay, so that would be the third one that we had listed. So we'll say 2 negative and 2 imaginary. Looks good. All right, so taking a look at this graph a little further, we're going to try parts C and D. So use the graphing calculator to determine the coordinates, okay, x's and y's, of the relative maximums and minimums. So these little humps and bumps, these high points and low points that we have on the graph, we're going to let the calculator find those exactly. So this one kind of looks like it's a height of 3 based off the graph, but we're going to figure out the height exactly by letting our calculator kind of do the work. So if we just take a look at the graph itself, it looks like we have 2 maximums, 2 high points, kind of top of mountain peaks or hills, and we only have 1 minimum. All right, so we're going to let the calculator do the work. Back on our calculator, we're going to try to find maybe this first maximum, okay, on the left-hand side. And we're going to do a process that's kind of similar to how we found x-intercepts. You know how you had to pick a left point, pick a right point, and then take your guess? We're going to do that same thing. So we're going to hit the blue second button and then trace. That's going to bring up our kind of go-to menu for anything based off of a graph. And you have to be careful as to which one you select, because there is an option for a max and a separate option for a min. So if we're going to find this maximum first, we're going to select number 4. So that little cursor should pop up on your screen, and we're going to scroll over to where this first maximum is located, at least where we think it is. All right, so hit the left button a few times and then hit enter. Hit the right button a few times, hit enter, and then go back to where you think it is and hit enter for your guess. So the word maximum should pop up on your screen, and the cursor should be stationary now as to where the high point is actually located. We're going to go ahead and write down the coordinate, the x and y value on our paper. Maybe we'll go to 3 decimal places. So I have negative 1.366, comma 2.848. Can you get those same values? Relatively close at least. Okay, we're going to repeat the process. Maybe we'll go ahead and find the minimum next, that little low point. So second trace, this time we'll do option 3. Move the cursor to where you think it is. Left a few times, enter. Right a few times, enter. And then take a guess. So I got 0.366, negative 2.348. Does that look about right? Can you guys try the last one? You got to find that maximum, that high point. Anybody get it? Probably not as involved as the previous 2, hopefully. Do we get it? I got 1, comma, negative 2. Did you get 0.99999? You can round it to 1. Okay. Mine's 1.0000002.
Rounding is a scam.
Is it?
It's overrated, and it gives untrue values. And that's not even a word, but I'm going to use it anyway.
Yeah. Actually, I forget which bank it is, but there's a certain bank that doesn't round to the 1,000th spot or 10,000th spot, like when you do money.
Yeah.
And if you don't round to, like when you get interest, if you don't round to that spot, there is a point in time where you start losing money based off your interest as if they were to round it. You would gain a few extra dollars or so.
I tell you, it's just big numbers.
Yeah, I know.
Save you money. Well, they don't save you money, they save the bank money.
Right.
I would never want
And that's why they don't round, so they save money. All right, so now that we found the exact coordinates of these maxes and mins, we're going to use those to our advantage to determine those increasing and decreasing intervals, kind of a throwback question. Let's go ahead and check those out. So if you were to trace the graph from left to right, your pencil would initially be going up until you reach the maximum. So in terms of our interval, we'd be increasing from negative infinity, okay, all the way to the left, until we reached the first maximum, which we labeled had an x-coordinate of negative 1.366. So that's where our increasing interval has to end, wherever that maximum is located. If we continue to trace, we would be decreasing from the first max to the next minimum. So we're going to start at negative 1.366, and if we have to stop at the minimum, that had an x-coordinate of 0.366. If we continue to trace, we're briefly increasing between min and max. So we'll throw in a U for the increasing intervals. So we'll go from 0.366, which was the minimum location, to the last max location, which we said was 1. And as you end your tracing, you're going to be going down forever to the right. So we'll throw in a U for decreasing, and we go from 1 to infinity. Okay, so as soon as we can find those maxes and mins, we can automatically determine where a graph is going up or going down. We're going to do something similar for part D, but instead of finding maxes and mins, we can go ahead and find those points of inflection, which are changes in curvature, changes in concavity. So as soon as we know those points, we can classify where we are concave up and concave down. Can we maybe refresh ourselves on where points of inflection happen on a graph? I'll give you a clue. There were 3 options that we can kind of roll through. Yeah.
Like multiplicity of 3.
Multiplicity of 3. Do we have any of those? No. Okay, so we don't have to worry about that one. Gonna keep going?
Multiplicity of 3 and the max and min.
Multiplicity of 3, the middle of a multiplicity of 3 and a max or min, but since we don't have a multiplicity of 3, that one's not needed either. And then the third one?
The relative minimum and max, minimum and max.
Yep, middle of min and maxes, which we clearly have, right? Because we identified that in C. So we're going to take these coordinates that we let our calculator find, and we are going to find the middle of them. So we need middle of, let's see, our first max, negative 1.366, comma 2.848, and the next min, which was 0.366, comma negative 2.348. How can we find the middle of those? They're a little bit more complicated than the ones we did previously because we had nice whole numbers. It was kind of easy for us to figure out the middle. How can we figure out the middle when they're more complicated? Like decimal values. Yeah? Find the average, the middle of the two. Okay, so we're going to add them together and divide by 2. If you were to add the x's together, what would we get? Can we realize that would be negative 1? This decimal would cancel out those decimals, so we're left with negative 1. And then if we divide negative 1 by 2, okay, take an average, that'd be negative 1/2. Okay, let's do the same thing for the y's. Add the y's together. You can use a calculator, but hopefully you won't need to for this one. We get 0.5 if we add them together. And divide 1/2 by 2, we'll get 1/4. Okay, so there's our first point of inflection. If we graph it, we're basically somewhere right here. Okay, where the curvature is changing. All right, now we have another set. We can go between the minimum and the second max that we found, 1 comma negative 2. All right, this one's going to be a little bit more complicated. Add the x's. We'll get 1.366. Divide by 2. Someone help me out. 0.683. Okay. So there's the middle of the x's. We're going to do the same thing for the y's. Add the y's. We'll get negative 4.348. Divide by 2. Negative 2 point something. Negative 2 point, yeah? 174. Good. All right, so graphically that's in the middle of this max and min. I know it's really cramped on your paper, but we're somewhere right in the middle. All right, looks good. So if those are the points where the curvature is changing, let's go ahead and identify concave up sections and then concave down sections. 1, 7, 4. Okay, so if you trace your graph until you get to a point of inflection, our first section is concave down, looks like an upside down parabola. So we'll go from negative infinity to the first point of inflection, which we had as an x value of negative 1/2. If we continue to trace to the next point of inflection, notice how that would be a concave up interval. Looks like a regular parabola. So we'll go from negative 1/2 to the next point of inflection, which we said was 0.683. And if we continue to trace, we'll be concave down, okay, upside down parabola, the rest of the way. So we'll throw in a u for concave down, and we'll go from 0.6833 to positive infinity. Okay, so very similar analysis. It's just that for C we were using maxes and mins, and for D we were using concave up, concave down. Okay. Are we doing okay with the calculator? Finding those spots? All right, we'll try the last question tomorrow.